All right, so not much to go over on this, but let's kind of just go over what we did on Monday. Cassidy, do you need the notes?
From last class?
Yeah.
I should know.
Okay, good. All right, so we did a bunch of talk about trig functions and especially like what they look like on a graph. So we talked about what sine, cosine, and tangent look like. Sine and cosine have that wavy-like structure and no asymptotes. But then when we got to tangent, we had some values where our function doesn't exist, where these asymptotes came about. So we had one every time we hit like a multiple of pi over 2. Okay, now what do I want to say about this? I was going to say something about it. Oh yeah, we talked about domain and range, right? So for sine and cosine, we said the domain was all real numbers. And the range was between -1 and +1 because, well, that's how high and low our function went, right? Any ideas on what the domain of tangent is? Or what x values work and what don't work? So let me write out the domain here. And remember, the domain is everything that can be plugged in. So what x values have y values? Okay, oh, yeah. 0 works, right? Definitely works. Pi, 2 pi, they definitely work. What about like pi over 12, which is like over here? That's an x value that has a y value, right? Okay, what about pi over 2? Does my function work there? No, right? So I think we're getting an idea of, okay, the function works everywhere except for pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. I'm gonna say the easiest way to do this, and let's think about this. It's basically everything except, well, any multiple of pi over 2, right? So if I multiply pi over 2 by any number, I'll get like, actually that won't work either, right? How about this? Odd multiples of pi over 2. Okay, what I mean by that is if I take pi over 2 and I multiply it by an odd number like 3, -1, -3, 5, 7, any of those numbers will give me one of those asymptote values, okay? So I don't expect you to memorize this. We'll actually talk about something weird in a little bit, but that's the domain of this function, right? Okay. What's the range of this function? What y values can this function have? Yeah, all real numbers, right? It looks like there's no y value that doesn't, that the function doesn't exist at. If I take any value on the y-axis and look to the right and left, it looks like the function is there. So the range here is all real numbers. Okay. Now, here's a big question. In the very beginning of our class, we said that a function is something that passes the vertical line test. So if I take a vertical line, move it from the right to the left of my function, it should pass the function only once, right? The function can't hit the vertical line twice. And that seems to really do work for my sine function and my cosine function. If I take a vertical line, move it from the left to the right, my function does pass the vertical line test. Okay, I'm gonna ask you a question. Does tangent pass the vertical line test? Actually, it does, doesn't it? I don't know what I'm going on about. It doesn't pass the horizontal line test, but so does sine and cosine. See, this is where I woke up kind of late, so I don't know what I'm talking about here. Okay, well, tangent does pass the vertical line test. I thought I was going to make a big point there, and I just didn't. Okay. Yeah. Yeah, we'll talk about that a little bit later. Okay, I'm going to tell you something weird about the domain here. sometimes we're not really interested in everything that happens at tangent. The really big thing about tangent is, well, the big shape of the graph, usually around 0, right? Smaller angles usually work. Sometimes we'll do something weird called restricting the domain, okay? Okay, and what this restriction does is we're basically just saying we're going to ignore everything except the part of the function that we really care about, okay? And usually what people care about are only this part of the function. So we kind of take away the other tangent values and we really kind of focus on the middle because that's kind of the more important thing to us. And we'll talk about why that's important later. I'll tell you it's because of the horizontal line test, not the vertical line test, which is what I was trying to talk about. But we usually restrict the domain to -π/2 to +π/2. Okay, that's kind of like the most important part of the graph. And I thought I was going to make a point there, but I'm kind of not. Okay. Any questions on tangent? All right. So on the quiz, I'm going to ask you to draw the one of these functions, okay? And what I'm looking for are several things, okay? The first thing I'm going to look for is that you labeled the x-axis, okay? So I want those specific labels from 0 to 2 pi. I want π/2, pi, 3π/2 clearly labeled on the graph. One other thing I want is to clearly label the values in the y-axis. Now for tangent, there weren't any labels because we don't really have any important points there, but there was important points on sine and cosine, right? So I'm really looking for that 1 and -1 on your graph, okay? Also on a test or quiz, I want you to plot important points on the graph. So I want you to show what values, what point values are. So for example, 0, 0, pi 0, and then these 5 points on sine and cosine. Okay, so I want you to plot those points very clearly. And then finally, I want you to show any asymptotes for the tangent function with dotted lines. I want you to clearly show where the asymptotes are. All right. And I think that's about it for trig graphs. Any questions on trig graphs? All right, and I think we are all done this section. Now, I will tell you that there are graphs for cosecant, secant, and cotangent. We don't really use them that much, and even in calculus, they're not used too much. So if you're curious, you can kind of take a look at those, Google them, but for this class and future classes, you probably won't need them too much. All righty, so we are about to start this new section, which I think scares a lot of people. We're going to talk about how to manipulate algebraic versions of our trig functions using these trigonometric identities. And there's a lot of these trig identities, and we'll talk about what that even means in mathematics. We're going to go through kind of the fundamental ones, the very basic ones that are used very often. But if you take a look at our textbook, there's actually a lot of these. A lot of people tend to give them out to students and tell them to memorize them. You do have to memorize a little bit, but I'll try to make the memorization a little bit easier to do throughout this class. But we are getting into this section that is a little bit scary. Okay. So before we even talk about what an identity is or what this is, you might see some symbols that look a little bit confusing. So let's just go over that first, and then we'll talk about other stuff, okay? Okay, so let's say I wanted to take a sine of π/3 and square the whole thing, okay? So what this is telling me to do over here is to take the sine of π/3, figure out what that number is, and then square it, right? When we write this in textbooks and actually just in normal life, writing out the parentheses and squaring it looks a little bit bulky, okay? So sometimes what we do is we take this square and we just move it in between the sine and the angle, okay? So whenever you see sine square of π/3, all that's saying is the same thing as what's on the left. Okay, so don't worry if you see the square in a weird place. It's just saying to square what result you get when you do the sine of that angle. Okay, same thing with the other trig functions. If you ever see a square in between the sign or the function and the angle, it's just telling you to square it. Okay. Okay. Let's talk about what an identity is. We've talked about some identities before, but I didn't really talk about what it actually meant. We talked about the reciprocal identities, right? Now there's more of these. There was one that said sine theta equals 1 over cosecant theta. Why didn't I write that identity on this page? So I told you had to memorize that one, right? Yeah, right. It's the same identity as this one, right? They kind of go hand in hand. Cosecant and sine are related. They're opposites of each other, inverses of each other. But since I already wrote it up top, I don't need to write it again, right? So there are other identities that are the reciprocal identities, but I only put the important 3 up top. Okay, and they're called identities because they don't just work for theta, they work for anything, right? So if I plugged in pi over 3, cosecant of pi over 3 would equal 1 over sine of pi over 3, right? So it works for any angle, any symbol, anything like that. Cosecant of something equals 1 over sine of something, okay? Okay, we talked briefly about the tangent one. Remember when we introduced tangent, we said it was the y value over the x value? Well, sine is the y value and cosine is the x value. So that's why we have the tangent one, okay? Now, cotangent is cosine over sine. Now, I'm going to tell you, don't actually have to memorize this one. You do have to know it, but I'm going to tell you this one you don't really have to memorize. Why is that?
It's
Yeah,
because
go
it's,
through. Oh,
it's the
yeah,
same
Amara.
thing as tan.
Oh, what did you say, Amara?
I said because it's the same thing as tan.
Yeah, right. So we agree that, okay, cotangent is the same thing as tangent, but it's flipped over, right? So we can kind of combine the fact that tangent's the flip of cotangent and the definition of tangent to get to this one, okay? So you do have to know this one, but if you really don't want to memorize it, you can just memorize tangent and flip over for cotangent. Okay. Now, finally, going on, we have these things called the Pythagorean identities. We haven't talked about these yet, but these come up a lot in trigonometry, calculus, things like that, and they're used quite often, okay? Now, why do you think they're called the Pythagorean identities? Oh, what does it look like? Yeah, it looks like the Pythagorean theorem, right? And this is actually how these come about. We're not going to prove it, but whenever we take something squared, add it to something squared and having it equal to, well, something else, it looks like the Pythagorean theorem, okay? And that's kind of how I memorize what these are, okay? Now, we'll do a little bit of work with these, so we're not going to talk about this too much in depth right now, but I'm going to tell you that the only one, you have to know all of these 3, but if you want to reduce your memorizing, you really only have to memorize the first one, okay? So you do have to know all of them, but I'm going to tell you there's a way to get to the other 2 by just memorizing the first one, okay? And this is how we're going to do it, okay? So let's say I only memorize this, sine squared plus cosine squared. Oh gosh. Oh no. Equals 1, and I didn't memorize the other 2. What I would do is do something weird, but stay with me here. I'm going to divide everything by cosine squared. Okay, so I'm going to divide this by cosine squared. I'm going to divide this by cosine squared. And I'm also going to divide this by cosine squared. All right. What do you think sine squared divided by cosine squared is going to be? Well, what's sine over cosine? Tangent, right? So, I mean, they're both squared, so this would become tangent squared. Okay. What's cosine squared over cosine squared? 1, right? Something divided by itself is 1. And then what do you think 1 over cosine squared is going to be? Take a look at your reciprocal identities. The secant, right? Secant squared, right? So I started with the first one. I just divided by cosine squared on everything. And I actually got the second identity, right? Now the one and the tangent squared are flipped, but it's addition, so it doesn't really matter. But you can go from sine squared plus cosine squared equals 1 to the second one, okay? Now, okay, let's pretend I didn't know the third one. I can still remember sine squared plus cosine squared equals 1, but this time I'm not going to divide by cosine, but by sine, okay? So I'm going to divide everything by sine squared. Okay, sine squared over sine squared, well, it's same thing as cosine over cosine. This is going to be 1. Cosine squared over sine squared is actually going to be cotangent this time, right? And then 1 over sine squared is going to be cosecant. Okay, and well, we've landed at the last one. So really all you do have to know is the first one, but you do have to either memorize or be able to get to all 3 of these Pythagorean identities. Okay, so out of everything, we already memorized the first reciprocal identities. We kind of know the tangent one, and all you really have to memorize at this point are the Pythagorean identities. So you do have to know all these. So I'm going to say memorize in quotes. Okay, you should be able to get to all these, but definitely you have to know these. Okay. All right, any question on these identities before we start kicking it up a little bit? All right, let's go to the next page and get to stuff that I think makes everyone a little bit scared. Okay, so whenever you're given a question that tells you to simplify something using the trig identities, it's kind of hard at first when you look at it, but there's actually several tricks that we can use for different types of questions in this section that make things a little bit easier if you know the trick, okay? So taking a look at this example here, this is telling us to write each expression in terms of 1 trig identity. So there should only be a sine, cosine, tangent, cosecant at the end, shouldn't be multiple, or a constant, so some sort of number. Okay, so the answer can either be like sine, cosine, tangent, cosecant, something like that. Or it could be like 5, 7, 15, something like that. Okay. Another thing in this example is we don't want trig identities in the denominator. Okay, so if we don't want anything in the denominator. Okay, so that wouldn't be considered simplified either. Okay. If we take a look at part A, we have tangent times cosine. Well, tangent and cosine are 2 trig identities, not 1, so it definitely needs to be simplified a little bit more, right? Okay, now when you take a look at this, we have a lot of trig identities to use, right? We have a bunch using tangent, so it's kind of weird, like, okay, which one do I use, right? I'm going to say for these examples where we're taking a big clump of stuff and we're trying to simplify it, I'm going to tell you the trick, okay? So the trick for these types of questions normally is to change everything into sine and cosine. Okay, let me write that out. Change everything into sine and cosine. Okay, and the reason we do this is because there's a lot of identities involving sine and cosine, not so much the other ones, okay? And when we do this, we're able to reduce everything into 2 things that we know, and normally things kind of cancel out when we do this, okay? So this is going to be our trick, and it's going to make things a little bit easier for us to figure out what to do at each step. Okay, well, we have a tangent, which isn't sine and cosine. We have a cosine, which is there a way I can change tangent into sine and cosine? Yeah, tangent is sine over cosine, right? We basically have two options, right? We can say it's 1 over cotangent, which wouldn't help us. Sine over cosine does change things into sine and cosine. So let me change this into sine theta over cosine theta. Okay. Now the cosine on the right is already in terms of sine and cosine, so I'm just going to keep that multiplied over.